Okay, good evening everyone. We'll start today's session. So, I hope you have gone through the lectures for this week, and we'll solve some of the questions, and hopefully that will clarify whatever you have learned in this week. Yep, so we'll start with the problems. So the first question is find the Laplace transform of f of t is equal to 1. So we'll start with the definition of the Laplace transform. So what we have is f of t is equal to 1, and we want to find the Laplace transform of f of t. Okay, so Laplace transform of the function is the integral from 0 to infinity e raised to minus st f of t dt. Okay, so we know that f of t is equal to 1. So if we integrate from 0 to infinity e raised to minus st 1 into dt. So okay, so it is 0 to infinity e raised to minus st dt, and we know how to integrate exponential, so we can directly write e raised to minus st, and here constant is minus s, so we have to divide that by minus s 0 to infinity. And if we substitute the limits at infinity, the integral will be 0, and minus, if we put t equal to 0, so it will be 1 upon minus s. So that is nothing but 1 upon s. So we found out that Laplace transform of 1 is 1 upon s. Okay, so this was asked, so function is given, so the correct answer is A. Okay, so similarly you can find out the Laplace transform of so you can try the exercise. F of t is equal to t raised to n, and what is the Laplace transform of f of t? So here f of t is t raised to n, so you can find out by the similar procedure. Okay, yeah, so we'll go to the next question. So what is the inverse Laplace of 1 upon s? So this is so already we solved the previous question where we saw that the Laplace transform of 1 is nothing but 1 upon s. So we can say that 1 is equal to Laplace inverse of 1 upon s. So so this is just the definition of the inverse. So Laplace inverse of 1 upon s is 1. So yeah, this is the correct answer. So that was straightforward. Okay. Okay. We'll go to the next question. So what is the Laplace transform of f of t e raised to 80? So I think okay, correct. Okay, so this is we have to find Laplace transform of e raised to 80. So we'll start with the definition of Laplace transform of any function is nothing but integral 0 to infinity e raised to minus st f of t dt. Okay, so 0 to infinity e raised to minus st, and the function is given. So f of t is e raised to 80 dt. So this is the function that is given. Okay, so we can add the exponents, base is same, e. So e raised to minus s minus a t dt. Okay, so you can see that here instead of s, now we have s minus a, and it is nothing but the, you can see this is the Laplace transform of 1, but instead of s, so we already know that the Laplace transform of 1 is 1 upon s, but here we have s minus a, so instead of s we will get 1 upon s minus a. Okay, so that was the Laplace transform of e raised to et. Okay, so I hope this is clear. So the correct answer is s minus n. Okay, so we'll go to the next question. So if the Laplace transform of f of t is f of s, then the Laplace transform of e raised to f of t, then the Laplace transform of e raised to et into f of t is what? Okay, so what is given is Laplace transform of f of t is equal to f of s, and okay, so then what is asked is what is the Laplace transform of e raised to at f of t, that is asked. Okay, so we will again start with the definition. So we'll write the definition for this. So Laplace transform of the f of t is equal to integral 0 to infinity e raised to minus st f of t dt. Okay, so and this whole integral is given as f of s. Okay, so that is the first that is given to us, and next what is asked is what is the Laplace transform of e raised to at f of t. Okay, so we'll write the integral form. So e raised to minus st e raised to at f of t dt. Okay, so yeah. So we are so the question I will just repeat. If the Laplace transform of f of t is given, which is a capital F of s, then the Laplace transform of e raised to at f of t is asked. So we have written the definition of the Laplace transform for f of t, and which is nothing but the f of s, which is already given, and now we are finding out the Laplace transform of e raised to at f of t. So we wrote the integral form here, and if we add up the exponent, so it will be minus s minus at f of t dt, and you can see that this integral is already given, which is f of s. So here instead of s, s minus a is there, so which will be nothing but f of s minus a. Okay, so the Laplace transform, so if the we'll write if the Laplace transform of f of t is capital F of s, then the Laplace transform of e raised to at f of t is nothing but the f of s minus a. Okay, so whenever we multiply with e raised to at, that will be subtracted from the s, that coefficient or this the constant that multiplies the t will be subtracted from the s. Okay, so the correct answer is this one. Okay, I hope this is clear. So we'll go to the next question. Okay, so here the question is the inverse Laplace L inverse of this function is that dash. Okay, so we'll start with so we'll just separate into s minus 3. Okay, so what we will do is we will write this s minus 3 as let's say s minus 3 minus 1 upon s. So this is simple, so we'll just write as of now 1 1, because you can see that the both coefficient for this is 1. So if we do that, we will see that at the numerator we'll get s minus 3 divided by s into s minus 3. So that is nothing but 3 by s into s minus 3. So this 3 is coming as additional term, so we'll divide by 3 here. Okay, and so this we already saw that the Laplace transform of constant is 1 upon s, and Laplace transform of e raised to at f of t is nothing but 1 upon s minus a. So we can see that the similar form is whatever in the first term is similar. Oh, sorry. So which is nothing but f of s minus a. So f, capital F, is Laplace transform of f of t. Okay, so we can see that this first term is somewhat similar to this f of s minus a, and the second term is similar to Laplace transform of 1. So we can directly process or we'll just write step by step. So the Laplace inverse of 1 upon s is nothing but 1, and okay, so Laplace inverse of 1 upon s minus 3 is nothing but, you can see that whatever term that is being subtracted, which is a, it will appear as exponent here, so it will be e raised to 3t Laplace inverse of 1 upon s, and we know how to take the Laplace inverse of 1 upon s, so it will be e raised to 3t. Okay, so we now have the Laplace transform of 1 upon s, which is the second term, and Laplace inverse of s 1 upon s minus 3, which is the first term. So we'll just substitute that, and what we will get is Laplace inverse of 1 upon s minus 3 is equal to 1 upon 3 Laplace inverse of 1 upon s minus 3 minus 1 upon s. Okay, so which is nothing but Laplace inverse of 1 upon s minus 3 minus Laplace inverse of 1 upon s. Okay, so we already have the answer. With the first Laplace inverse is e raised to 3t, and the second Laplace inverse is 1, and we are taking the integral from, if we have this time axis, so we are taking the integral from 0 to infinity. So you can see that this one, actually we are considering that for positive time, this t the function is 1, So this and then we are not worried about the what happens in the negative time. So this one we can replace with the heaviside function, which is t. So this is nothing but the step function. Okay, so what we can write is, actually this whole term can be multiplied by h of t, but as per the options we'll just write that. So h of t. So this is the answer, and you can see this is the first one matches, where the 1 upon 3 e raised to 380 is here. So 1 upon 3 e raised to 8 is here, and minus 1 upon 3 h of t is the next term. Okay, so this is the correct answer. So I hope this is clear. Is there any question in this? Okay. Then we will go to the next question. Okay, so the next question is find the Laplace transform of sine 80. So we will start with the definition. So what we want is Laplace transform of sine 80. Which is nothing but integral 0 to infinity e raised to minus st sine 80 dt. Okay, so the thing, first of all we will integrate this e raised to minus st sine 80 dt, and then we will substitute the limits. Okay, so we will use the so we have two terms. So we have we'll use UV rule for this. So we'll take the integration by parts. So first we will rearrange these terms. So integral sine 80 will and e raised to minus st dt. Okay, so first of all we will write the first term as it is, sine 80, and we'll write the integral for the next term, which is e raised to minus st upon minus s, then minus derivative of sine 80. Derivative of sine 80 is into cos 80, and we have to take the integral of this term, which will be e raised to minus st divided by s square, and then plus, then instead of we'll just write the integral now, which will be, we have to differentiate this term a cos 80, which will be minus a square sine 80, and next term will be as it is, e raised to minus st upon s square dt. Okay, so what we have is sine 80 e raised to minus st divided by minus s minus a upon a square cos 80 e raised to minus st, and you can see that this okay, so this one you can see that the next term, which is a square integral sine 80 e raised to minus st dt, which is same as what we have started with. Yeah. So Raghavendra, you just joined. So what we are doing is finding the Laplace transform of f of t sin at. So we have started with the definition and then used the um, integration by parts to perform this perform this integral first, and then we will substitute the limit from 0 to infinity. Okay, so we can, after doing this integration by parts, so we got the two terms, and then the third term we got some constant, and then the integral term is same as what we have started with, so it is nothing but I. Okay, so sin 80 by minus s minus a by s square cos 80 e raised to minus st minus a square by a square, and this term we'll just write as si. Okay, and what we will do is we'll take this term on the left hand side, so we'll have 1 plus a square by a square I equal to sin 80 by minus s. Okay, and minus a by a square cos 80 e raised to minus st is there. Okay, so whole term multiplied by e raised to minus st. Okay, so I is equal to, so we can we can write this and then on taking this term on the right side will be s square divided by s square plus a square, and sin 80 divided by minus s minus a by s square cos 80 e raised to minus st. Okay, so finally we have got this integral, so we will substitute the limit from 0 to infinity, and then we will get the Laplace transform. So the Laplace transform will be, so if we substitute the t equal to infinity, you can see that this term will become 0, and the whole term so the whole expression will be 0, and at t equal to 0 we will get let's say minus s square by s square plus a square, and in bracket if you put t equal to 0 the first term will be 0, and minus a by s square, and then cos of 0 will be 1, and e raised to minus st which will be 0 sorry 1. So the Laplace transform will be, you can see that minus sign will minus will be plus, and a square will get cancelled, and it will be a upon s square plus a square. Okay, so we saw that Laplace transform of sin 80 is nothing but this one. Okay, so it was just for exercise we solved this, so if you practice this you can directly use this expression. So okay, so the correct answer is a upon sin square, yeah, it's a upon a square plus a square. Okay, I hope this is clear. So what we will do is the inverse Laplace of 1 upon a square plus a square. So we just saw that similar expression, so where we saw the Laplace transform of sin 80 was a upon a square plus a square. So the Laplace inverse of a upon a square plus a square will be sin 80, and we can take out this constant, so it will be, so we can just divide both sides or just take it out, and L square of Laplace inverse of 1 upon s square plus a square sin 80, and that way sin 80 by e will be the Laplace inverse of 1 upon a square plus a square. Okay, so this one was pretty straightforward once we know that the Laplace transform of sin 80 equal to 1 upon a upon a square plus a square. Okay, so this is the correct answer, sin 80 upon a. Okay, so we will go to the next question. So find the inverse Laplace of this expression using the convolution theorem. Okay, so you can see that this we know the how to get the Laplace inverse of 1 upon s, and we also know how to get the Laplace inverse of s square plus a square. Now what is given is these two terms are now multiplied. So how to get the Laplace inverse, and to get this we will be using the convolution theorem. So we'll see what is it. So let's say we have the f of t, and f of t function is given, and if we take the Laplace transform of that, we are getting some f of s. And if we let's say have another function, let's say g of t, and if we take the Laplace transform of this, let's say it is g of s. Okay, so we know that these two terms how to take the Laplace, but now we are interested in taking the multiplication of this and find the inverse. So what is the so the same thing we can write as f of t is equal to Laplace inverse of f of s, and g of t is nothing but the Laplace inverse of g of s. Okay, so what is the Laplace inverse of f of s into g of s? So because that's what is asked, so we know how to take the individually the Laplace inverse. So how to get this Laplace inverse if the multiplication is given? So you can use the convolution theorem, and you can derive it like if you have time, but for time's sake we'll just write the equation. So if we have the multiplication in the, let's say, s domain or Laplace domain, then that will result into the convolution in the time domain. So this will be f of, let's say we'll say tau, and g of t minus tau d tau. Okay, so this is the, so here you can see that this f of tau is nothing but the Laplace inverse of the first function, and then g is nothing but the Laplace inverse of the second function. And if we know individual functions Laplace inverse, this integration we can compute and find the Laplace inverse of the multiplication. Okay, so this we will use here. So what is asked is Laplace inverse of so we will write this, interchange this, because you can see that f of tau we can directly use, and then g of t minus tau, so we have to delay this next function. So we will just rearrange. So we'll take this, we'll put s next and s square plus a square first, just to simplify calculation, and into 1 upon s. Okay, so that is nothing but 0 to t. So f of t, so we just saw that Laplace inverse of 1 upon a square plus a square is nothing but 1 upon a Laplace inverse of a upon a square plus a square, and this is nothing but sin 80 by a, and Laplace inverse of 1 upon s is nothing but 1. So if we use that expression here, so we can write the first term, we can write the Laplace inverse, which is f of tau, as the sine a of tau divided by a. And next term, we have to write tau minus g of t minus tau, but it is just a constant, so that way we have simplified just by rearranging the terms, so we don't have to take this delayed term. Okay, so this is a pretty simple integration. So we'll write Laplace inverse of 1 upon s square plus a square 1 upon s equal to integral 0 to t sine 80 tau. Sine a of tau by a into 1 d tau. Okay, so we will take this integral sine a tau 0 to t d tau, and which will be integral of sine a tau is minus cos a tau divided by a, and we'll substitute the limit 0 to t, so it will be minus cos 80, and then this a, let's say we multiply out and take out, so it will be a square, and if we substitute 0, and minus will become plus 1. Okay, so we got 1 minus cos 80. Okay, so I hope you understand how we we know how to take the Laplace transform of individual term, so we use this rule, like you can say we use this convolution method to get the Laplace inverse, and yeah, so this is the answer, 1 upon a square 1 minus cos 80. Okay, 1 minus cos 80, 1 minus cos 80 divided by okay, I think I wrote some, okay, 1 minus cos 80 by a square, 1 minus cos 80 divided by, let's say this is write the a square, so this is the correct option, I forget writing a square here. Okay, so we'll go to, is there any doubt in this question? Okay, so if there is no doubt, we'll go to the next question. Okay, so the next question is on the Fourier series. So the question is the Fourier series expansion of the sawtooth waveform f of x is equal to x in minus x to x of period 2 pi gives okay, so this gives the series. Okay, so let's say this is the given series, so given the series, the sum is equal to, so this series is given, and we want to find this sum using this definition, f of x is equal to x. Okay, so we have given f of x is equal to x for x is between minus pi to pi, and what is asked is 1 minus 1 upon 3 plus 1 upon 5 minus 1 upon 7 and plus is equal to what, so this sum we want to find out. So first we will so they have given the way to do this, like compute this sum. So first of all we have to use the Fourier series expansion of f of x, and then we'll see how to get this. So if we have f of x, the Fourier series expansion is a0 plus summation n is equal to 1 to infinity an cos nx. So here I'm writing nx because the period is from minus pi to pi, but for in general case you have to write n pi x by L, or some modifications you have to do. So just period is given as 2 pi, so we can directly write nx here, bn sin nx. Okay, so this is given, and so a0 is 1 upon 2 pi integral f of x dx, and then we have to integrate it over this interval minus pi to pi. Okay, and if we do that, what we will get is 1 upon 2 pi integral minus in pi to pi, and x is given x dx, and you can see that x is the odd function, and if we take the area under this curve, which will be negative on the left side of this y-axis, and then the area will be positive on the right side, or the integral values. So that way, if we add up, it will be 0. So this is because the x is odd function, and we will determine now the an. So an is nothing but 1 upon pi integral minus pi to pi f of x cos nx dx. Okay, so an is equal to 1 upon pi, the limits is minus pi to pi, and f of x is x, so x cos nx dx. Okay, so you have any question?
Sir, for odd function a0 and an both are 0, right? Only bn will exist.
Yeah, right, correct. So here also x is odd, and cos nx is a 1. So if we multiply this, the resultant will be odd function. So similarly, an will be 0. Yeah, and if we go for computation of bn, so which will be 1 upon pi integral minus pi to pi x, so which is f of x into sin nx dx, and you can see that this is odd function and this is even. So in that case, the multiplication will be even function, so we can integrate this. So we'll use the integration by parts. So first we'll write x as it is, then integrate sin nx, which will be minus cos nx, and then n is multiplied, so n will come in the denominator. Okay, so minus, and then we'll take the differentiate this x, which will be 1, and we have to integrate this next term, which will be minus okay, sin nx, and n will be n square. Okay, so and then if we go for next term, this term derivative will be 0, so we don't have to go there. So minus pi to pi. Okay, so what will be the answer? So you can see that sin n pi, if we take this second term, anyway will be 0 if we put the pi or minus pi. So this term is of not of interest. So we'll just deal with the first term. So if we put pi, it will be pi, then minus cos nx, and okay, and minus pi, and minus cos of n pi, it is cos n pi divided by n. Okay, so cos of n pi minus, okay, so here okay, so we'll take this pi out and then cancel out, so it will be 1 upon 1, let's say we cancel that, and we got minus cos of n pi, and minus, this will be minus minus minus, so this whole term will be minus minus plus, and then minus cos n pi, cos n pi divided by n square. It's yeah, n only. Okay, so this is minus 2 by n cos n pi. Okay, and cos of n pi is equal to minus 1. Okay, I will write it somewhere. So an is equal to minus 2 by n cos n pi. Okay, so here I write cos n pi is equal to 1 if n is even, and equal to minus 1 if n is odd. Okay, so this will be, so okay, so I will not write the okay, so let it be this way.
Sir, minus 1 to the power n, you can write cos n pi.
Yeah, that way we can write. Okay, so an is equal to minus 2 by n minus 1 raised to n. N it's even. Okay, that will work. Or yeah. So if we write this expansion, which is we are doing the f of x is equal to summation bn sin nx, and what we got is bn is equal to minus 2 by n, and minus 1 raised to n sin nx, and this f of x is already x, given x. So what we can see is this sign will alternate as we change the n, and if we put, let's say, x is equal to 0, so this whole term will be 0 on the both and right and left side. Let's say if we put x is equal to pi by 2, because we don't want any complex, like any value which is like fractional. So if we put pi by 2, so what we will get is pi by 2, and minus let's say 2 we taken out. Okay, let's say plus 2 we taken out. Then okay, I will write the expansion. So first term will be n is equal to 1, and which will be minus, then minus 1 raised to 1 plus the next term will be minus 1 upon 2, and then minus 1 raised to 2, and sine of pi plus we'll have minus 1 by 3, minus 1 raised to 3 sine 3 pi by 2, and so on. Okay, so pi by 2 is equal to did I miss something? Okay, let's see. I think I might have missed. Bn is 2 upon pi. I missed somewhere pi. Okay, let me check. it is correct only. Okay, so we'll proceed and then we'll see. Okay, so this 2 is there, and the first term will be 1, then the next term will be, so sine of pi is 0, and so this term will be 0, and next term will be, this will be -1, so this will be minus, so minus, okay, so this will be 1/3, and so on. I think I messed up somewhere, because this whole term will be present only at odd locations, and that way this plus minus will not come. Okay, so if we want to get that, we have to substitute here instead of n pi, we have to, oh sorry, I think yeah, we are correct only, no problem. Okay, so here this term will be minus will be plus, and then sine of 3 pi by 2 will be negative, so sorry for that. Yeah, okay, so this is minus, and then you can see that it will repeat after that. Okay, okay, so it will be pi by 4 is equal to 1 minus 1/3. That will be that is the answer. So this pi by 4 is the answer. So I will just check whether I missed somewhere pi, so just consider this, or this might be the correct answer, but as of now we have got this, so you can verify whether I missed somewhere this pi, and just check by yourself. So okay, but the procedure will be the same, and you can try out yourself. Okay, so the next question is for the function f of x, which is -2 and 2, so -2 for the x less than 0, and then +2 for the next part. So you can see that this is odd function, so f of minus s is nothing but f of minus f of x, and then what is asked is the an. So if we write the an, which is nothing but minus pi to pi 1/pi e raised to, so this is not f of x cos of nx dx. Okay, see this term is even, and the function that is given is odd, so the resultant function will be odd function, and if we integrate odd function from minus pi to pi, it will be 0. So an is 0. This was straightforward. Okay, so we'll go to the next question. Okay, so this question is just about what is the function, whether this function is even or odd function. So we have f of x is equal to minus x raised to 4 plus x square. So we can write f of minus x, and you can see that it will be doesn't change. So f of minus x raised to 4 will be same and same. So f of x is equal to f of minus x, so which is nothing but the even function. So this one also was straightforward. So we'll go to the next question. Okay, so next question. Okay, so the next question is f of x is equal to sine hyperbolic x, and interval is given. The value of the Fourier coefficient an is. So similarly, if we write the integral an is equal to f of x e raised cos of nx dx, minus pi to pi. You can see that f of x here sin hx, which is odd function, and this is even. So odd even will result into the odd function, and then this integral will be 0. So this is again pretty straightforward. Okay, so then we'll go towards we saw some examples on the Laplace and Fourier. So we'll talk about, like, solve some problems in partial differential equation. So this is the equation given, and then obtain the partial differential equation for this. So you can see that z is a function of x and y, and in this case we are supposed to remove this constant and write this expression in terms of partial derivatives. So what we will do is we'll say dou z by dou x, which will be, we have to differentiate ax plus by, and we are saying that x and y are independent variables. So when we differentiate with respect to x, the derivative of y with respect to x is 0. So if we do that, what we will get is this derivative will be 1 plus b into 0, and that is nothing but a. So we can see that dou z by dou x is, so wherever a is there, we can replace by dou z by dou x. And next we will differentiate this z with respect to y, and that will be dou z by dou y ax plus by, and that will be 0 a into 0 plus b into 1, and that is nothing but b. So we can replace b with b by dou z by dou y. So what we have dou z equal to dou x plus by, and a can be replaced with dou z by dou x, and we'll just write x in front in order to avoid that confusion whether it is under differentiation or not. And b we will write as dou z by dou y. So this is the differential equation for the given equation. Okay, so I hope the procedure is clear. So we'll go towards the next example, which is somewhat, it will take some time. It is looks a bit complex. So obtain the partial differential equation for this equation. Okay, so this is you know that this is the equation where this tells that we have the some location. Let's say this is some location in the 3D plane ABC, and we are computing the distance from this of the xyz, and this distance is constant, and this is nothing but the sphere. So this is the equation of sphere, and then let's say this is x, y and z. So we'll have some surface, and you can see that this we can write for given, let's say given any point, so there will be the corresponding z value. So we can actually, there are so we can write z is a function of x and y, and then we can solve this whole equation. So we will treat x and y as a independent variable, and z is the dependent variable. So if we first, what we'll do is we'll differentiate this whole equation with respect to x. So what we will get is 2x minus a plus, so this next term there is no x, and then y we are treating as independent variable, so that we will write 0, and 2 z minus c dou z by dou x equal to 0. Okay, so So we'll cancel out this 2 at x minus a plus z minus c dou z by dou x is equal to 0. Okay, so we can see that the whole so it doesn't matter whether it is x or y, the equation is symmetric in terms of x and y. So we can directly write y minus b plus z minus c dou z by dou y. So just replace x with y, that will work, and instead of a we are writing b. Okay, so we got till here. So what we'll do is we'll differentiate once more with so this equation we will differentiate with respect to x, and remove this constant a, and the second term we will differentiate with respect to y. Okay, so we'll see after differentiating what we will get. So first term, if we differentiate with respect to x, the term that remains will be 1, and 1 plus. Okay, then we have to differentiate the second term. Okay, so I will just write the thing will be symmetric in terms of x and y. I will just differentiate for x with properly x minus a plus z minus c dou z by dou x is equal to 0. Okay, so this will be 1 plus this term we will use the multiplication rule, so we will first keep this as it is and then differentiate with the next term dou square z by dou x square, and plus now we will differentiate this first term, so that way b dou z by dou x, and again we have this next term is dou z by dou x, and this will be 0. Okay, so you can okay, so what we have is 1 plus dou, so I will write this term first, dou square dou z by dou x square, and let's say we'll take this term on the right. We'll see in a minute why we are doing that. Z minus c dou square z by dou x square. Okay, so what we will write, dou z by so you can see that this term is independent of x or y, so if we keep it on the right, we can write 1 upon dou z by dou x square divided by dou square z by dou x square, and similarly it is symmetric in terms of y, so we can write dou minus if we do the same procedure, what we left with dou z by dou y square divided by dou square z by dou y square. Okay, now we can equate these two terms. So we have 1 plus dou z by dou x square divided by second derivative of z with respect to x, which is nothing but 1 plus dou z by dou y bracket square divided by dou square z by dou y square. Okay, so we can simplify this. We'll just multiply this term by both sides, and this by this term also on both the side. So what we will get is dou square z by dou y square 1 plus dou z by dou x square, and on this side we'll get dou z square by dou x square 1 plus dou z by dou y square. Okay, so you can see that it is whatever differential equation we got is symmetric in x and y, So whatever x is there on the one side will be replaced on the by y on the both side, another side. Okay, so this was the differential equation for this sphere that we consider. This is for sphere. Okay, so I hope the procedure was clear. So we'll go to the next question. This is also one question that obtain the partial differential equation for this is general function. So here you can see that there can be any number of constants, or this function can be any like anything. So we don't know about this, but we just know that f z is a function of okay, so we'll write some capital F. So let's say we use z only. Z is a function of x and y. Okay, so what we'll do is we'll differentiate this first z with x, and so if we differentiate z with respect to x, what we'll get is dou z by dou x. Okay, so first we'll differentiate this first part x, which will be 1, so we'll get f of y upon x, and next we'll differentiate the second part, which will be f dash of y by x. So we are using chain rule here, and now we have to differentiate this y by x. Okay, so what we have is f of y by x plus x into f dash of y by x, and y will be treated as constant, so y will come out, and then 1 upon x, if we differentiate, that will be minus 1 upon x square. Okay, so what we have is y upon x, and this will be minus y by x f dash of y upon x dou z by dou x. Okay, so this is the first equation that we got just by differentiating z with respect to x. So what we can see here is this term is there, and even if we differentiate this z with respect to y, this similar term will come, and that term we are planning to replace in the next step. So z is equal to x into f of y by x. Okay, so what we will do is differentiate z with respect to y, dou z by dou y, and x anyway is a constant, so it will not be affected. So the next we have to differentiate the function, and we are using the chain rule again, y by x. Okay, so if we differentiate this, x will come out as it is, and then if we differentiate with respect to y, it will be 1, so we got f dash of y by x, so dou z by dou y. So you can see that we can now replace this derivative of f by dou z by dou y. Okay, so so what we have found out is dou z by dou x is equal to f y by x. Okay, the next is minus y by x, and then there is a derivative of f, and this was the first equation. The second equation that we determined is this one, which is nothing but f dash of y by x. So now we will substitute 2 in 1. So if we substitute this here, so what we'll get is the dou z by dou x is equal to f of y by x minus y by x, and this we will substitute by dou z by dou y. Okay, Now if we so what we will do is we will multiply by x, and you can see that x into f of y by x is given. So if you multiply both side by x, so you can see that x will appear, and this we can replace with z. So let's multiply by x. So x dou z by dou x into f of y by x minus y dou z by dou y, and this is nothing but z. So what we have is z is equal to x f of y by x. So we'll use this, and so x into dou z by dou x is equal to z, this is z, and minus y by y into dou z by dou y. Okay, so we'll take this partial derivative on left, x into dou z by dou x plus y dou z by dou y is equal to z. Okay, so this is the partial differential equation of if z is equal to x into f of y by x. Okay, so I hope this was clear. So we will, if it is there any question? Okay, so we will solve the next question. The equation dou u by dou t plus 2 into 1 plus x square dou cube u by dou x cube, u is, so you can see that this is the third order derivative, and the coefficient, if we see, the coefficients are the functions of independent variable, and not the function of u, which is the dependent variable. So this is the linear differential equation, and order is 3. So this is the third order linear PDE. Okay, so we'll go to the next question. Okay, so the next question is the formulate the PDE from z is equal to x plus 1 into y plus 2, and we can use dou z by dou x equal to p and dou z by dou y equal to q. So z is equal to x plus 1 into y plus 2. So dou z by dou x, if we differentiate with respect to x, so what we will get is y plus 2, and if we differentiate this z with respect to y, we will get x plus 1, and if we substitute this into the expression for z, so you'll get z is equal to, the first term x plus 1 is nothing but dou z by dou y, and the second term, which is y plus 2, which is dou z by dou x, and we can use this identity given dou z by dou y, which is nothing but q into dou z by dou x is, is p. So z is equal to p into q. So z is equal to p into q is the correct answer. Okay, I hope this is clear. So we'll go to the next question. So in one dimensional heat equation, dou u by dou t is equal to alpha square dou square u by dou t square. The value of alpha square is, okay, so we can, so this we can obtain by determining, like we can derive the equation for the heat conduction. So let's say we have this and let's say this is the area is A, and let's say this is the x-axis, and this location is x, and this is x plus delta x. So you can see that the thickness of this slab is delta x, and let's say the heat that comes at this location is at x location, and this is the rate of heat conduction uh, per unit area at x, and this is x plus delta x location. So this is the, let's say, heat conducted at this location is x plus delta x, q of x plus delta x. Now what we can do is we can use the Taylor series expansion to determine this, how much the heat is conducted at x plus delta x. So you can see that it is, if we do the expansion, it will be dou q by dou x and into delta x. So this is, we are not considering the higher order terms because we are saying that delta x tends to 0, so we are not considering the higher order terms. So this is the heat that is conducted. So q is the heat conducted per unit area per unit time. Okay, so let's say the net heat that is conducted is q, and then the net heat that is going out is qx, x plus delta x. So q you can write as q at x into area. So this is the rate of heat in, or you can say this is nothing but q that is going in, and then q out, which is nothing but q at x plus delta x, which is q at x plus delta x into a, and that is nothing but qx plus dou q by dou x into delta x into area. Okay, so what we can write is okay, so the difference between the inflow and the out influx, or inflow of heat and outflow of heat, or influx of heat and outflux of heat, it will be the heat will, the difference will lead, or the difference between this heat or energy conducted out in and out will be stored into this slab. So what we can write is q in minus q out is equal to the rate at which heat is stored. Okay, so if we see that let's say the mass of slab is nothing but m is equal to, say, rho, which is density, into the volume. So the volume is nothing but area into delta x. So this is nothing but rho a delta x, and then let's say the specific heat capacity, like the heat required to increase the heat, the 1 unit mass by 1 degree is, let's say, c. So the, let's say we'll say this the rate at which the heat is stored, okay, so the rate at which let's say, or we'll say energy instead of heat, because heat will be at the boundary, at which energy is stored is nothing but the d dt of let's say the energy that is already, let's say, stored, let's say q stored, and dt is so how much heat will be stored if the let's say mass is m and c and t. Let's say t is the temperature. So this is nothing but dt of m. We already saw it is rho a delta x, rho a delta x. And here we are just interested into the particular location. So instead of taking the total derivative, we'll write the partial derivative, because we are fixing the location and not varying the location. So we are not moving with the location. So t will be the, so here you can see that t will be the function of time as well as the location. So we are fixing the x, so we are taking the derivative with only with respect to time. So this will be the rate at which the energy will be stored, and the rho, let's say, assume to be constant, and a will come out, and delta x also will come out, and t by dou t. So this is the rate at which energy is stored. So if we rewrite this equation, so the left hand side we got the expression, and the right hand side we have q in and q out. So we'll write the whole expression. So rho a delta x dou t by dou t is nothing but q in minus q out. So q in is q x into a, x into a, minus q out is nothing but this expression, qx plus dou q by dou x delta x into a. And if we substitute, like if we simplify it, this term will get cancelled with this one, and we'll be left with dou q by dou x. And let's cancel this x and a, which is common on both sides. Oh sorry, this c is missing. Okay, c is, I did not write. So rho into c dou t by dou t. Okay, and this is the q is the heat conduction. So you can see that we'll use the Fourier law of heat conduction. So q is nothing but minus k dou t by dou x. So this expression we will use now, and if we substitute that here, so what we'll get is rho c dou t by dou t is equal to minus minus plus dou square. Okay, so dou x, let's say we substitute minus k dou t by dou x. Okay, so if we, I will just, I don't, okay, so this is, we'll just simplify and write it here in short. So what we have is the dou t by dou t is equal to, so this minus minus will get cancelled, and what we will be left with k by rho c, and then this will if we taken together will be dou square t by dou x square. So you can see that this is the constant k by rho c, and which is nothing but alpha square. So alpha square is nothing but k by rho c. So this is the correct answer, k by rho c. Okay, I hope this is clear. Next we'll see another question on partial differential equation. So this is the equation given, and is called, okay, so let's see what is the Laplace equation. So Laplace equation will have dou u square by dou x square plus u square by dou y square is equal to 0. And heat equation we just derived, so it was this equation. So instead of t we can write u also, so we'll just stick to u. Dou u by dou t is equal to, let's say, alpha square dou square u by dou x square. And if you see the wave equation, which will be dou square u by dou t square is equal to c square dou square u by dou x square. And then if we see the Poisson equation, which will be dou square x square plus dou square u by dou y square is equal to f of xy. So even though this Laplace and Poisson equation look similar, but if the right hand side is 0, it's called Laplace equation. If it is non-zero, it is the Poisson equation. So this given differential equation is the Poisson equation. So this is the correct answer. So I think that's all the questions I